Hi, my name is Dániel, and as it's mentioned, I've been talking about structured bindings and how to analyze them. I want to jump right into the middle. So basically, this is how a structured binding declaration looks like. As you can see, it starts with the auto keyword, which can be optionally surrounded by attributes, CV qualifiers, or reference qualifiers. And then it is followed by a list of identifiers, where each identifier will represent a specific value inside the initializer, depending on the type of the initializer, which can be basically, like the initializer can be three different types. The first is being an array. In this case, the identifiers will represent the elements inside the array, with the first identifier referring to the first element and the last identifier referring to the last element. And if we want to rewrite this snippet so that we actually understand what the structured binding declaration does behind the scenes, it would look something like this, where first the new temporary variable is introduced, which is going to be the copy of the array in this case. And then you can see the identifiers are really just names or symbols referring to specific elements inside that copy of the array. And of course, if any reference qualifier is used, basically the temporary variable will be a reference type instead of it being the copy of an array. And then the identifiers will look up the values from the original array throughout this reference. The next case is when a structured binding is created to some instance of a class. In this case, the identifiers will refer to the fields inside the class in the declaration order. And as in case of as with the previous case, first a new temporary is going to be introduced that holds the copy of the instance, and then the identifiers will look up the fields from this copy. And of course, if a reference is used, it's going to be the same as with arrays, so that the new temporary will be a reference. And the third and the last case is binding a tuple-like type, where compared to the other two cases, this one is a bit more different, because here, actually, after the temporary variable is created, for every identifier, a new variable will also be introduced, where the type of the variable is going to be determined by the std tuple element helper, and the initial value will be returned by std get, with the corresponding index, of course. And then each identifier will be a reference to the variable with the same name. Now, of course, if the binding is created by reference, then both the temporary and the variables will be reference types, so they will access the value in the original tuple. Before we jump into how to analyze these with the Clang Static Analyzer, I'd like to take a step back and talk a little about the Clang Static Analyzer. So basically, this is an open source tool built on top of the Clang frontend that performs symbolic execution to find bugs, and it produces path-sensitive bug reports. So in practice, if we take a look at this toy example, we can see that there's a stack allocated variable called x, and the value of x is assigned to y. Now at this point, we know that x holds some undefined or garbage value, and the analyzer is able to detect that. Like it says, the assigned value is garbage or undefined, and it's also able to backtrack where that value comes from. So if you take a look at the first node, it tracks it back to the declaration of x and says the problem originates from x being declared without an initial value. And basically, the way the analyzer achieves this is that first it takes the source code from the user. Now this needs to be either a C, C++, or Objective-C code, or as far as I know, if you're a real enthusiast who regularly writes Objective-C++ code, then you can also use the analyzer to find bugs in your code. So after the source code has been supplied, the analyzer is going to invoke the Clang frontend to construct the abstract syntax tree, or AST, which is basically a structural representation of the source code. And after the AST has been constructed, it's still going to rely on the Clang frontend to construct the control flow graph, or the CFG, which represents the order in which the specific AST statements are evaluated. And after that, the analyzer is going to take the CFG, traverse it, and evaluate every statement inside that, and try to model what the state of the program looks like after the statement has been evaluated, and constructs the X-loaded graph, which basically contains, like every node in the X-loaded graph contains the state of the program after a statement has been evaluated, and whenever it finds any issues, it's going to backtrack the X-loaded graph to figure out where that issue comes from, and it produces a path-sensitive bug report, which usually Like it can either be an XML document that looks like this, like you can see the source code and you can see the specific labels that tell you what the problem is at that point, or it can also be some text representation in the form of compiler warning messages and compiler notes, as you've seen a couple of slides before, if you remember that. So after seeing all these data structures and stuff that happens in the analyzer, you might wonder, like, why do we even want to support these structured bindings? Like, it seems like there's a lot going on. Basically, there are two different cases that can happen if a specific feature from a language is not supported. I mean, like, technically there are three, but I don't think that the analyzer crashing or resulting in a stack fault is actually a valid case. So let's break it down to two, where the first is false positive warnings. This is a real-life snippet that we received as a bug report on GitHub, when basically a developer takes a Q pair of an int and a Q shared pointer and decomposes it into X and P. And you can see that the int is initialized to 42, and the shared pointer is initialized to a null pointer. And then the value of the shared pointer is assigned to possibly another shared pointer. And we can see that this is actually okay, because that other shared pointer will also be a null pointer. But the analyzer reports this warning like a function call argument is an uninitialized value. And if we look at the node, we can see that it backtracks it to the P identifier. And it says like something.second.d has an uninitialized value, that basically that unnamed object before the .second is supposed to be the temporary variable that's created at the point of the structured binding declaration, if you remember that. So basically we know that this is a problem with the lack of support for structured bindings. And the other case is false negatives, when in this case a stack allocated array is decomposed into X and Y. Now we know that in the array every element is some uninitialized or garbage value. And we also seen that in such cases, the analyzer is able to report a warning that an uninitialized value has been assigned to something. But in this case, the only warning we get is that A has been given a value which is not read. So it fails to detect that actually A has been assigned an uninitialized value. So now that we actually seen some examples that why we need support for structured bindings, let's jump into how to achieve this. Basically, what we need to understand is how a structured binding declaration looks like in the AST and the CFG, because these are the data structures the analyzer is mostly going to work with, like during the traversal phase and then the value evaluation phase. Basically, a structured binding declaration is going to be a declaration statement which holds a decomposition declarations, where the first child of the decomposition declaration is the expression that creates the temporary variable, and then you can see every identifier is represented in the form of a binding tag, which hold an expression, which expression, if gets evaluated, represents the value that belongs to this identifier. And if you take a look at the control flow graph, you can see that only the variable initialization is in the control flow graph. That means the analyzer will automatically create the temporary variable. However, it's not going to do anything with the binding decks. And if you take a look at some more concrete example, like in this case, an array is being decomposed into B1 and B2, and then later the value of B1 is assigned to a new variable. We can see that the array is initialized, the temporary array is created by an ArrayInitLoopExpr, and then every binding tag contains an array subscript expression, which returns the corresponding element of the array. And then later, when the identifier is used, it's going to be a declare reference expression to the binding tag. And in the control flow graph, as you can see, after the temporary has been created and the structured binding declaration has been evaluated, the next statement is the reference to the identifier, and this is the point where we actually want to use some trick to manually look up the value that this identifier represents. And the way it's going to work is we know that we are visiting a declaref expression that holds a binding tag to the identifier. So we are going to take this declaref expression and extract the binding tag from it. Now we know that the binding tag contains an array subscript expression, and it also provides a direct access to the temporary array that has been just created. And we know that the array subscript expression contains the current index of the element that's being looked up. So at this point, we know the array from which you want to look up the value, and we know the index of the element we want to look up. So we can just tell the analyzer, like, take the temporary array and then look up the value at this index from your internal memory, and this way we can bind that specific value to the B1 identifier. Now, in this other case with binding to data members, everything is going to be the same. There are only some minor differences, like a construct expression is used to initialize the temporary, and the binding index hold a member expression that refers to the specific field that identifier represents. And the control flow graph is obviously also going to be exactly the same. And whenever we look up the values, instead of extracting an array subscript expression, we extract the member expression and the field, and then based on the temporary variable and the field, we can tell the analyzer to look up the specific field that belongs to this identifier, and then we can bind that to it. And the last example is binding a tuple-like type, as if seen in the first half of the presentation. In this case, it's a bit different because there's a new variable introduced for every identifier. Now, apparently, these variables are in the CFG, so the analyzer will automatically create and initialize them, so there's nothing to worry about here. And during the lookup phase, you basically take the binding deck, which provides a direct access to this new variable, and then we just tell the analyzer, like, okay, this binding deck refers to this variable, just take the value of that variable and use it when the binding is referenced. Now, I'd like to get a bit more into some implementation details, mostly around ArrayInitLoop expression. Basically, this expression is used whenever an array has to be copied implicitly somewhere in the source code, which includes like implicit copy or move constructor of a class with an array member, whenever a lambda expression captures an array by value, and of course structured bindings. Now, basically, this expression looks like in the AST, like it holds the source array and holds the initializer that is used to copy every element in the source array. If you take a look at the CFG, you can see that only the initializer is in the CFG, and it's only there once. So it doesn't matter whether it's a 1-element array or a 100-element array. The ArrayInitLoop expression is not going to be unrolled in the CFG. So we need to do some manual hacking to achieve the unrolling. And what we want to do here is we separate POD arrays and non-POD arrays. POD arrays are like arrays that hold ints, for example, or floats, or other plain old data types. In that case, what we want to do, if the array is sufficiently small, we create a copy manually. And that means we know that the original array is stored somewhere in the analyzer's memory. So we are going to create a new array and then manually hand copy every value into the new array. Or if the array is too large and we cannot do that, we use a lazy compound value, which basically is a creation of a pointer to the original array, because we know that whenever a POD array is copied, there are no side effects. So we can just simply create a pointer and then tell whenever we need to look up the value from the copy, we actually dereference the pointer and look it up from the original array. And in case of POD arrays, in case of non-POD arrays, we know that constructor calls are involved for every element construction, and constructor calls can also have side effects, so we must evaluate the constructor calls to get an accurate modeling. However, we cannot always do that, and in those cases, we use something called a conservative evaluation, which basically means that specific constructor is not going to be evaluated. We just mark the region of the object, like we cannot reason about this region, and that's it. Now, basically, for POD arrays, the method that's being used is selected based on the region store small array limit analyzer option, which defaults to 5. So it means that if the array has more than 5 elements, then we are going to create a lazy compound value, otherwise a member-wise copy. And for non-POD arrays, the method is decided based on the analyzer max loop option, which basically an option that prevents the analyzer evaluating the same statement multiple times. Like initially, imagine that you have a recursive function that calls itself every time. And obviously, we don't want to get stuck into an infinite loop. So there is this fail-safe option, which says like if the same statement is visited more than 4 times by default, the analyzer will abort the evaluation and fall back to conservative evaluation. Now, in case of constructor calls, we don't even attempt to call the constructors if we know that we can't finish calling the constructor for every element. We just skip straight into conservative evaluation. And basically, the way it's going to work, like, we don't know the current element of the array that's being constructed. So we need to somehow figure that out, and that's why we use program state traits, which basically allow us to attach arbitrary data to the program state and then carry that data through the program states. So we are going to create two state traits. The first is the index of the element that is currently under construction, and the second is the size of the array. And based on the index of the element, we can figure out what the parameter to the copy constructor is. And then we can call the copy constructor with this parameter. And based on the index, we also see whether we reach the end of the array or there are still elements left to evaluate. If there are still elements left to construct, we increment the index and force the analyzer to evaluate the same statement again. And we select the new element and again check if we reach the end of the array after evaluating the constructor. And if we see that we reach the end of the array, we let the analyzer keep going with its regular evaluation, like let it jump to the next statement. So basically at this point, the analyzer can copy non-POD arrays. However, there is some problem with it because it turned out that initially the analyzer wasn't able to construct these arrays. So that was also something we needed to take care of. But the idea is exactly the same, so I don't want to get into too much details. We just call the constructor for every element, only that in case of array construction, the constructor will have the type of the array, and based on the type, we can figure out the size, so we can only use one state trait. We don't need to store the size of the array. And then, of course, if an array has been constructed, like the constructor for every element has been called, we also need to call the destructor for every element. And this is a bit tricky because in case of destructors, we only know that we invoke a destructor, but we also know that the destructors are called in a reverse order, so the last element of the array is going to be destructed first. And we also know that the elements of the array are somewhere inside the analyzer's memory. So we can use the dynamic extent API, and we can tell the analyzer, like, there's this region which contains an array of elements, and every element has this type, and the dynamic extent API has a method to figure out how many elements are in that memory region based on the fact that it's an array and based on the fact that it knows the type, so that by using this API, we can set the initial index of the first element that's being destructed, and then we can decrement this index until we reach the beginning of the array. And when we reach the beginning of the array, we know that every element has been destructed, and we can let the analyzer jump to the next statement. Basically, I'd like to mention some quick thing about holding variables. Like, originally, they weren't part of the control flow graph. So initially, this is how a control flow graph of a binding to a tuple-like type looked like. So the holding variables had to be added, and this is how the control flow graph looks now. And one thing to keep in mind is whenever you introduce a new variable to the CFG, you most likely have to also introduce it to the liveness analysis inside the static analyzer. Otherwise, they might be flagged as unused, and the garbage collector of the analyzer might erase them from the analyzer's internal memory. So I don't know if you have any questions at this point.
Any questions? Good.
Okay, so if there are no questions, then let me have a quick summary. So basically, after these changes, the analyzer supports structure and bindings, but basically this is what the presentation was about. And we saw that it also comes with some unwanted advantage, mostly like the support for non-POD arrays has also been introduced, like construction and destruction. And also, we see that some parts that are involved in copying the array are also used in lambda captures. So we also have a better reasoning about arrays captured by lambdas. And the same ArrayInitLoop expression is used for implicit copy and move constructors. So we also have a better coverage for classes with fields, with array fields. And also it turned out that the control flow graph modifications were beneficial for the data flow analysis developers because they also use the same CFG modifications. And all of these changes are live since Clang 15. So if you haven't been trying that out, now is the time, or maybe you've been working with a lot of C++17 or post-C++ 17 code, and you were extensively using structured bindings and you missed the lack of support when now it's been introduced. So just try it out, have a look at it, and if you happen to find any bugs, just report them on the LLVM GitHub page, and hopefully it will be fixed one day. So I'd like to thank you for your time and your attention, and enjoy the rest of the conference.
Thank you. So, any questions? Damien, I do have a question for you. I just wonder, what's the overheads of your tool? Say, if I apply this to a project with hundreds, thousands lines of code on a typical developer desktop, what kind of time overheads are we talking about?
As far as I know, there were no significant increase in the time of the analysis when we tested the changes. So I can't tell you exact numbers, but it didn't introduce a huge overhead.
Okay, cool. Any questions? So what's the next step for these tools? Is there any features you're really keen on to add on top of it, or anything, any future plans for that?
Well, not at the moment, but if something comes up, I will obviously look into that, but I don't have anything planned for now.
Okay, cool. So any more questions? All right, so now let's sing a speak again, and our next talk will start at 11 o'clock.